All right, AP Statistics. So now we're going to take a look at a rule for defining outliers. This is not a totally universal rule. It's the most commonly accepted rule, but there's no just clear way that we define an outlier. I mean, it's a data point that is kind of far away from the rest. Well, how far does it have to be to be considered an outlier? There's a couple different ways, but this is the most common way of figuring that out, and it's actually the one that our calculator used for identifying outliers. What we do is we use that IQR, the interquartile range we just figured out, and it's called the 1.5 IQR rule. It's really uniquely named, but that's part of the formula, so it makes it nice. So any observation is an outlier if it falls more than 1.5 times the interquartile range. So it's not, it's a 1.5 interquartile ranges above the third quartile or below the first quartile. Don't get that confused with the median. So low outliers would happen any value below Q1 minus 1.5 times the interquartile range. And high outliers would happen any point above Q3 plus 1.5 times the interquartile range. So looking at this in a data set, so we've got highway fuel economy ratings for 25 forerunners, and we've got them graphed there. So we've got our Q3 and our Q1 there, so we can and they've subtracted those to figure out our interquartile range. And so interquartile range is there. If we go 1.5 times that below 22.2, so Q1 minus 1.5 times, so 22.2 minus 1.5 times that interquartile range will give us a lower threshold. So any data value below 21.6 would be considered an outlier because it's more than 1.5 interquartile range below Q1. And so if we look at this, we do have a low outlier. That would be the threshold. And this is a somewhat arbitrary decision point, but it's kind of nice to have an agreed upon definition. And then we can do the same for the upper end. We're going to go 22.6 plus 1.5 times that interquartile range and get that upper cutoff. So 23.2, we've got another outlier up on that high end. So the cars with fuel economy ratings of 21.5 and 23.3 would be considered outliers by that rule. The other kind of most common rule is to look at like a number of standard deviations from the mean. So depending on 2, 2.5, 3 standard deviations from the mean, different people will say that's kind of different levels of outliers. But we won't use that definition. So why do we look for outliers? Well, they may be inaccurate. It may be that something went wrong in that data collection process, and in that case, maybe we could take that into account and remove that from our data set. So that's one thing. They can just indicate remarkable occurrences. So if we see some individual is an outlier, that may be just a remarkable performance, or remarkably bad, depending on what direction it is. And then just to be aware of them because they heavily influence some statistics like mean, range, and standard deviation. Those are all not resistant measures of center and spread. So, all right, next thing we can move on to is making box plots. And so box and whisker plots, you may have done these before, but they use a 5-number summary. The 5 numbers they use are minimum, quartile 1, Q1, median, Q3, and maximum. So we need to figure out all those for our data set. So similar process. Min and max, we haven't done that, but those are pretty obvious. And those help us form our box plots. We kind of represent those visually. Box plot is a visual representation of the 5-number summary. So how do we make a box plot is we find the 5 numbers. And then this, you can just draw the box plot right as it is, but what they're going to say is identify the outliers. So you can actually show outliers separately in a box plot to make it clear. that they are outliers, and so that's I don't know, sometimes you'll refer this referred to as a modified box plot, but generally that's what we want, is the one where it shows outliers. So and you'll see that in a second. So we draw an axis. Find the outliers, draw and label an axis. So we get an axis to work on, make sure we have a label on it, scale it so that it goes from the min to the max, and is consistent scaling in between. So we draw a box for our between Q1 and Q3. That's our box part of this, and the median gets marked in the middle of that. So we have a little line in the middle to indicate the median. And then we draw whiskers. So the whiskers go, if you're going to do this modified method, it go all the way to the last point that isn't an outlier. So if we're in it, this is if we're going to show this separately, because then what we do is we show the outliers as these little like dots or asterisks, mark those as separate points. So we go up to the max. If there were no outliers, you would go all the way up to your maximum value, but if not, you go up to your next highest value to kind of show this is where most of my data is. Also, there's a point out here rather than just drawing an extremely long line in both directions. And so that box plot, that displays kind of the quarters of the data, 25% of the data, 25%, 25%, 25%. You can kind of see a little bit of a shape through it. It's definitely not the best graph for showing shape. We can see, this data seems fairly symmetric from it. You can see if it's skewed, if one of the whiskers is longer than the other, significantly longer than that might indicate a skew. But it's really nice for like showing a quick little distribution of the data, where the center is, what the inner quartile range is, the middle 50%, the range, also any outliers on the outer edge, and they go really nicely next to each other. If you have like one data set, you can just stack up box and whisker plots right next to each other really nicely. So be cautious. They do not display each individual value in a distribution. They really just sum up quarters of the data, and they don't show gaps, clusters, or peaks. So that's kind of showing it back here with the dot plot. So box and whisker plots, a quick way of showing distribution, not necessarily the most the best visual picture of it. I'd say the histogram probably wins that competition. Doesn't preserve original data like the stem and leaf plot or the dot plot, but a quick way of showing some distribution, and it's nice that that does specifically call out those outliers. So at this point, you should be able to do all those things.